Hello, this lecture is about special features that you need to consider when you want to conduct realistic groundwater models. I picked two features to highlight especially. The one is dealing with the solute transport, and to be more specific, with the advective transport in solute transport models. We will learn a bit that this requires special care. It's a non-trivial numerical task, depending on the scheme you're dealing with. And I will introduce you to a couple of important vocabulary dealing with groundwater models on solute transport. And the other feature I want to discuss in detail is the handling of fractures. There is a great number of numerical tools to specifically deal with fracture flow, the combination of porous and fracture flow. And you will have fractures in almost any kind of groundwater scenario you're considering. And depending on the situation, there are different numerical tools to incorporate those fractures, which often are hydraulically important, into your model. But first, let's start with advection. And it is just simply, first of all, important to consider that advection is a non-trivial process to model. You have numerical methods which are just by definition unstable for modeling advection theorem, right? And because, well, if you look here on the right corner, what advection simply means it is shape conserving transport processes, as you hopefully remember from earlier lectures. Considering this is our initial condition, if there is no diffusion, we have pure advective transport, which means the whole shape is simply transported to the right if we consider we have a flow from left to right. Here I'm modeling in a temperature pulse, but you could do the same thing with an concentration, solid concentration pulse, or whatever. The problem remains the same independent of the property you're transporting. And although we fulfill, the stability criteria we got to know in the last week, the numerical solutions might seem unstable. So by definition, they are stable, but they, for example, show violated boundedness, artificial oscillations, and especially numerical diffusion. So let's take a step back and consider just mathematically what's happening here. So you might remember the advection diffusion equation again. In the mathematical lecture, I did this for the concentration of the solute. Here I'm doing this for the temperature, but as I said, independent of what kind of variable you're looking at, it's the same game. And usually we would have here the diffusive term, but I don't want to model here the diffusion. I simply want to discuss the advection. So I skipped that part of flux. So we simply have the change in time of my property. Here it's temperature. And this is balanced purely, there are no sources, nothing else. It's purely balanced by the advective flux through the surfaces of my control volume. Now I can even simplify this to 1D, so that means on the left-hand side nothing is changing, but I can also assume that my velocity is constant, so I'm taking all that out of the derivative, and then I simply have the change of temperature over space. Right, so this is a very, very simple equation, and all the problems that are occurring with the numerical simulation of advection already occur in this simple 1D case. Right? I mean, you can't even simplify it any further. It's a constant velocity. It's a 1D problem. It's just change in time, first order versus or balanced by first order change in space. It doesn't get any simpler than that, and still we have numerical problems. So let's take a look on how you could tackle that kind of problem. So the idea here is, so if you remember back to the mathematical lecture, so this kind of numerical partial differential equation is called a hyperbolic type. Doesn't need to bother you, but Just remember, all those kind of hyperbolic PDEs experience those kind of problems. And one term or one method you will hear a lot is upwind. The idea of upwind is very, very simple. So consider, again, you know, this kind of sketch from before. So consider we have a flow from left to right, right? We're in a 1D scenario, so we have a flow from left to right. And we know all the temperature distribution at our time t. And now you want to, you know, have the calculation for the subsequent time step, t plus dt. And we want to know it at the point x. Again, there is no diffusion, there are no sources, it's purely advective. So if we have a flow from left to right, you might consider, well, whatever I have as a temperature on this point x, it has nothing to do with the value here, because the flow is from left to right, there is no diffusion, nothing. So what I do is I approximate my derivative in space, simply considering the information I have upflow or upstream. So going back contrary to the flow direction and taking the information, well, of course, at the same position on the time step before, and whatever comes from the left side, right? So this is what is approximated here, right? On the left-hand side, nothing changes. It's my derivative in time. I take it at the position for the future time step at my current time step. So this is all fine. This is my unknown. All other parameters and variables are known in this equation. So this is my unknown. I will later reformulate this equation to obtain this kind of value. All the other values here are known because it's an explicit time step I'm using here. Well, doesn't matter, that was the topic of last week. What important is now this term here, right? I'm not taking any centered in space, like also considering the value over here or so. No, I'm doing upwind. Means I'm taking the value at this point, so this is this here, and I'm taking the value at this point, which is upstream, and then I can describe my flow. So this looks, right, that sounds very obvious, very straightforward. Well, okay, I have a flow from left to right, so only I'm considering all my values on the left, and I don't care about what's on the right because I haven't been there just yet. If you do this in a first order scheme, the numerical solution will look like on the right, and this is what we call numerical diffusion, right? So if you look here on the left, again, this is what we would have considered, right? Pure diffusive problem, shape conserving. This is our initial conditions. We have a flow from left to right. After some time, it should show up over here. However, if I now compare my numerical solution upwind first order to my analytical solution, well, you probably are not very delighted by that point of view, because you see, well, we're not estimating the maximum value correctly. And well, this almost looks like a normal distribution, right? So it has this shape of a bell curve. And this is what we associate normally with diffusion. But we are not solving diffusive terms. We're only solving advective terms. So this kind of diffusive behavior, what is occurring here, is not the physical process of diffusion, but it's numerical diffusion. Right? So the definition written up here means that the fluid exhibits a higher diffusivity than the true medium. And here it's especially obvious because there should be no diffusion at all. So everything we see is due to numerical diffusion, right? If you also have a diffusive process, it might be, a bit harder to see, but here it just took it very placative example so that you directly see what numerical diffusion means. Okay, and well, so you could be considering saying, well, okay, at least the position of the peak is kind of estimated correctly, but well, the maximum value and everything is not very delighted. But now you can say, because you have now already some experience in modeling, you say, well, that was a first order approximation. We could go higher orders. So let's go to second order. So how this would look like. The idea is still the same. I have a flow from left to right. I don't care about everything downstream because there is no information has been arrived so far. So all I'm considering is what is happening upstream. But now I'm second order, so in first order I consider those 2 points. Now I'm second order, so I'm considering more points. So I'm also taking this information here into account. I won't go through detail, all those values can be analytically determined. Left-hand side is the same as usual. This is my unknown, all other parameters are known. And you just see, okay, I'm doing my finite differences approximation here. Doesn't care about the details so much. Just important is up 1 second order. I'm just considering more points. And this is what we come up with. Again, on the left-hand side, this is our analytical solution. This is what we would expect. This is our initial condition. This is what we should expect. And now you see here in the dashed line, this is what we get with up 1 second order. You might say, well, okay, that's better than first order. What is it? We are overshooting. We are violating boundedness, right? The peak is now a bit far to the right. And we still get that kind of bell-shaped behavior, though much narrower now. So we reduced maybe numerical diffusion a bit. But again, we violate boundedness. It's a personal opinion. You can argue before, for and against it, pro and con, if that's better or not. But it has its benefits and its drawbacks. Now we can go even further. We can go to a third order, which I didn't write down here as the equation because it just means considering more and more points, which are weighted differently. Remember that it was second order we just had. Now we're going to third order. Well, that looks quite okay. We're still violating boundedness. We have this overshooting, but we're more centered now, right? We're getting pretty much peak and position correctly. The width of the peak is quite well approximated. So yeah. And of course, this is still upwind. If you deal with advection, there are a lot of different schemes, flux correction, and whatever they are called. They're also methods trying to reverse, to estimate the numerical diffusion effect and then reverse it. So, bunch of possibilities. But, I'm making you familiar with a few methods here today. Another important fact is, I want to show the influence of the initial conditions. I do everything similar to before. I'm only changing 2 points. The shape of the input signal and my spatial dimension. It's the same time scale. Okay, I'm just changing my spatial scale. I'm just changing my velocity accordingly. On this is just, I don't have this rectangular shape anymore. I have more of a, more smooth peak signal. The analytical solution, well, it's still shape conserving, right? So I'm just moving the same structure to the right. Not a big deal, you would consider. But this is how it looks like numerically. Upwind first order. For the rectangular signal, we said, oh, wow, that's all full numerical diffusion. Well, okay, there is still a diffusive behavior, right? We're still overestimating here. We have a bit of diffusive fluxes. There is no overshooting. Well, we're still losing something, right? We're not conserving here in terms of energy. But, well, there is a difference, right? I only changed the shape and the spatial dimension. That's all I did. It looks much, much better. Now we go for second order. Remember, that one was terrible. Overshooting, violating boundedness, tendency to be overestimating the flux. Well, that looks perfect, right? Wonderful shape. Third order. Can't get much better than the second one, right? Let's go back. Doesn't change much, right? So we have here the peak value, very well estimated, no overshooting, much centered. Great. I only changed the shape of the input and the spatial scale. So what I want to take you from that is you can have, other points of modifying your numerical result or numerical accuracy, the stability of your model, besides the algorithm, which you, if you're not a programmer, can't change anything anyway. Right? And just want to say is, if you want to practice a lot what we did from last week, take a few of those examples and discuss accuracy, adjust boundedness for those kind of samples. It's a good exercise. Right. That was the upwind scheme. But when you're working on solid transport or general transport problems a lot, you will learn about another method, or read about another method, better to say, which a lot of people are using. And this is based on, it's called point cloud model, Marcus model, Lagrangian points, traces, particle models, whatever. They're all based on the process or on the idea I will explain from now on. What we have done so far is the Eulerian perspective. All right, so you're considering like you're sitting on the bank on the river and you're watching the water passing by. So this is, you have a position out of the system. You're sitting on the side and you have everything static moving around you. The Lagrangian perspective is a bit more of those kind of point or Marcus ideas, means you're inside the system, like considering sitting in a boat and you're relatively moving or looking at the particles moving around you as you drift down the river. Right, and the combination of both, of course, numerically, we always have this Eulerian perspective. So we have our general coordinate system, our numerical grid. But the idea of all those point cloud particle models, whatever you will call it, is combining both perspectives. So you include points which are moving as boats through your system relatively to your Eulerian grid. So what we want to do is this combination. There are also other methods. Yeah, if you go really advanced numerical ideas of mesh-free methods or things like this, where you kind of skip this Eulerian grid and you're only considering points, discrete particles moving relatively to each other, right? The different fields, maybe not so much in groundwater modeling, but if you go towards rock mechanics or stuff like this, or landslide modeling, those discrete particle models will become very common in these kind of fields. Again, here we're still trying to attack this troublemaker advection. All right, so there we're more in those particles, point cloud models, combining. But what I want to summarize here simply as Lagrangian markers. With a fixed Eulerian grid means we have those kind of boats which are flowing with the flow field through our Eulerian grid, our static mesh, and those kind of boats transport information. And depending on where my boat is, I'm extracting information going back to my Eulerian grid. So how this whole thing works is you place usually randomly, if you start with an initial condition, but can also be centered depending on your scenario. So you place your Lagrangian markers within the grid, and those kind of points are advected with a flow field, right? So these are your boats flowing through your river. But those molecular markers are associated with physical properties or variables. That could be, for example, contaminant concentration, but could also be something like fluid behaviors, like fluid density, fluid viscosity, which are dependent on the tracer concentration or things like this. And what you do is, of course, you want to know the information on your Eulerian grid points. So you are interpolating the concentration values, or whatever their markers hold as properties, to the grid nodes. You do your calculation on the grid nodes, and if it's necessary, you do the interpolation back with updated variables to the markers. The whole idea about this is that you have much more markers than Eulerian nodes, right? You're not doing any calculations on the markers. The markers are just really flowing with your flow field, so they take over the advective part. And through the interpolation of the different markers to the grid nodes, you're kind of solving those advective behavior. All right, so here in black, we have our Eulerian grid. All those blue dots are my markers, which are relatively moving through my here 2D mesh. Now I have my grid point A, Y, J, pardon, and this is surrounded by some kind of region of interest, which I can define as I like. So you can make it larger or smaller, depending if you want to have a more local or a much wider interpolation. And now I'm interpolating all those markers based on their distance to my grid point. Right? If a marker is really close to my grid point, that means it holds, a lot of true information to this, to my local point here. If it's further away, it has a less strong relationship to my grid point over here. Right? So I'm interpolating, for example, doing some distance weighting. That can be linear, but you could consider, depending on the numerical method you're applying, any kind of shape, right? You could throw in here, for example, a bell shape weighting function, right? So based on the normal distribution, which in the closest surrounding would weight the nodes much more, further away much less, right? But it wouldn't be a linear relationship. It would be some more bell-shaped relationship, and then depending on the bell shape, your region of interest would vary. But this is the idea. You have your markers, and whatever kind of weighting scheme you're using, you're interpolating this value from the markers to the grid points, and if necessary, vice versa, right? So let's say this holds a concentration value, and I want to know now the concentration at my grid point. I would calculate, I would interpolate from all the nodes, from all the markers around my node, interpolate the concentration at this point, do whatever I need to do with this concentration. For example, calculate diffusion, right? So some of the concentration has diffused, and then I would interpolate this diffused concentration back to each marker. Then I would calculate the flow, so the marker position would be updated based on my local flow velocity, and then I'm doing the next time step. Okay, and I have maybe new kind of marker distribution in my region of interest, and then I would again interpolate back and forth. So which means it's just simply I'm not solving the advective terms in terms of a hyperbolic PDE here. I'm solving my advection by having those points which are moving with the flow field. And then simply through interpolation, I'm getting the information from those advective points. So this sounds very straightforward, but it also maybe already sounds not trivial. It strongly has its huge benefits, okay? Because you're usually avoiding numerical diffusion, and you have no accumulating errors between markers and nodes, right? For the interpolation. However, interpolation is also numerically cumbersome. It is associated with computational costs. Also, you have to update your marker's position, right? So you have to estimate the flow velocity at the marker position, which might also require some interpolation. right? And also consider if you really have this back and forth interpolation. So as I said, like you're solving the diffusive term on your Eulerian grid and then updating back the tracer concentrations on the points. This then again might cause numerical diffusion. But those kind of systems are especially helpful if you not need to do this interpolation back and forth. For example, if you have a problem that is dominated by advection, right, and okay, the diffusion that might take place is negligible because, for example, my flow velocity is so high, then those kind of point cloud models are a really good way to consider, right? It's so, for example, if you have contaminant transport, maybe not through the water but through the air, and where we have high flow velocities, then those kind of point cloud models are often applied. But also in groundwater modeling, this is can be applied. It has its sense, has its use, and that's why I think it's important to know for you. So when we want to conclude advection in a general term, is simply for you, first of all, to remember advection is challenging. Okay, it's not like, okay, let's do here solid transport and that's it. No, advection is crucial part of this, but advection is non-trivial. You need to have special care, special attention paid to this kind of problem. And this kind of scheme you have depends on the specific problem, right? And remember this simple change I did with the shape of my problem in the spatial dimensions. So try to avoid, for example, rectangular problems, right? These rectangular input shapes, something numerical codes usually don't like, these huge gradients or infinite gradients. This is very challenging to preserve in advection terms, and it often is not the realistic case anyway, right? If you considering introducing a tracer into the soil, there is some duration during the input. It's already diffusing as soon as you let it into the water, so you don't have this rectangular input signal that like theory would always like you to have. So there it's worth maybe smoothing it, getting a realistic input signal, and that will make advection much more accurate. And there is also an interesting point I want to have you is this numerical diffusion might even increase if you have smaller time steps. First of all, this is counterintuitive because you normally say, well, okay, if I get a finer spatial resolution, I get a more accurate result. Because, linear approximation, even if I'm implicit, everything we talked about last week, this will increase my accuracy. But here, because this numerical diffusion is something that occurs at every iteration, if I have smaller time step, I'm doing these calculations more often, and that might increase my numerical diffusion. Again, this is all those points. It very much depends on the scheme and how it is implemented in the program, but those are phenomenon that might occur, right? And if you have a new model or using a new kind of program, that's something, to get to know the program, try to simulate just simply a pure advective problem. Try to set the diffusion to 0 and just see what the program is doing and how well it's handling diffusive problems, advective problems. Pardon. The second specific feature of groundwater flow modeling, which requires our attention, are fractures. So fractures are usually known to increase hydraulic conductivity, can be associated with a reduced porosity, though this depends. There also is literature divided. It depends on a lot of different factors. At very much of the beginning, we had this idea of a representative elementary volume. We said we can incorporate fractures in those as long as the fractures are small compared to what we have as a pore subdomain. However, this is not usually, or is not always the case, put it that way. And sometimes also flow behavior and also transport process in fractures are fundamentally different than in the porous media, right? You can have turbulent flow in fractures. We can have different kind of dispersion, diffusion effects in fractures. And this is not just fractures, it can also be any kind of other like engineering constructions of tunnels, pipes, and stuff like that. So fractures is another point you need to pay special attention to when setting up a model when you're running simulations. So when we look at the fracture, the most simple approximation we can get is a plane plate model, which means you have two similar planes which are separated by some distance, which is the fracture aperture. And usually those fracture apertures are much smaller than the other two spatial dimensions, means the fracture is usually much longer and wider than it is thick. And this also usually causes the effect that we can neglect the pressure gradient vertical to the fracture surfaces. So you have this the representation here are your two plates. They're separated here. Well, this is overestimated, the aperture, right? And the spatial dimensions just here sketch, so it's not at scale. But we have some pressure gradient maybe in x and z dimension here, but the pressure gradient in y direction we can usually neglect, which then gives us the benefits that we can represent fractures by a reduced geometrical dimension. Means when you're in a 3D model, you can approximate a fracture as a 2D area, right? Because in this 2D area, you have a flow which is aligned in some way, but it's moving within this plane. Or if you go to a 2D model, your fracture is simply aligned, because it just has one preferential direction. This line can be oriented in any direction in your 2D plane, but it's just a line. We're not considering what is happening vertical to this line, right? Because the fracture aperture is usually much smaller than length and width, and therefore we can neglect the pressure gradient vertical to it. With this knowledge, there are different kind of ways to include fractures in your numerical model. So what we've done so far was pretty much effective porous media. So we considered the fractures as part of the porous media. And if you want to include, for example, regions with more fractures and regions with less fractures, you would set the parameters of permeability, porosity, or so on differently, higher in the area with more fractures compared to the area with less fractures. But we don't really know the exact number of fractures. We don't know their orientation maybe, or the fracture density, all those kind of parameters we don't know. We don't care about, because we are operating on effective values. Right? You can introduce something like anisotropy, so that kind of gives you an idea about the orientation of fractures. You say, well, it's more flowing towards north-south than east-west, or things like this. You can introduce anisotropy in the effective parameters, so mainly hydraulic conductivity. But you don't have to, and only if you have the required information. And still, that doesn't mean I know exactly where individual fractures are. All of those, so now we're going the way down, and we need more and more information pretty much about the fractures. So in the dual domain, you still don't need to know about specific fractures, but the numerical concept here is a bit different. So the idea is you have two domains with different parameterization, one representing your porous media flow, the other one representing the fracture flow, and both are coupled through the mass exchange. This gives different benefits and drawbacks. I will go through all that in detail in the following slides, but the concept is still based on Darcy's law. Discrete fracture models, on the other hand, really requires no information about the fractures. Right? So I need to know, where are my fractures? How are they oriented? How long are they? How wide are they? And then I need to parameterize it sometimes in either aperture width or on also something like hydraulic conductivity, permeability, which is associated to aperture width. And You really represent the fractures along credit lines, so you include them into your mesh, which then usually is associated with an expensive pre-processing, because the numerical crit generation needs to consider those fractures, and this is kind of cumbersome. Sometimes can be. But of course, this is a very, very accurate representation of your discrete fracture network. But it requires you to have a lot of information about your discrete fracture network. The embedded discrete fracture network is trying to be something like the best of two worlds. So you have your porous media flow in the background, and it kind of similar to the 2D dual domain approach puts the fractures on top of it, but you are in opposite to the dual domain approach, not separating it in a different domain. It's still operating in the same domain. But, and this is a combination of the association to the discrete fracture model, you specify each fracture individually, and you parameterize each fracture individually. Okay, so there is well, different approaches, and I will go through all those kind of approaches now in detail. But there surely are more methods, but those are the four which I consider the most common ones. So the effective spectrometer, this is what we have used about all the time. You know, Darcy's law is general valid. That's what you assume here, right? So there is no turbulent flow in the fractures usually, you know, all that kind of stuff. You only change the parameters, right? And if you have a fracture or a fractured area, you know, you assign a higher hydraulic conductivity, maybe higher porosity, and that's it. Okay, you don't go any further. What you can do is you can use anisotropy and hydraulic conductivity. So not being sure if everyone's familiar with what that means. If you consider a medium isotrope, it means the direction doesn't matter. Hydraulic conductivity, for as an example of parameter of an isotrope parameter, you know, is considered equal in all dimensions. If I have anisotrope hydraulic conductivity, that means I have a preferential flow direction, right? So this could be how I have some kind of layered media, or I have fractures as an example. That means here in this example, I would rather flow from left to right or right to left than I would fly vertical to it, right? And if I have a fracture, that's kind of reasonable assumption, because as I said, well, fractures usually do not allow, or have a reduced hydraulic conductivity, at least to say so, vertical to the fracture planes than inside the fracture. The dual domain model is quite old. It comes from the 1960s, and it has been improved since then in various types, right? It was originally developed for a flow, but now you have it for heat transport, also for advanced heat transport and transfer processes. You have it for contaminant transport. So there is a bunch of separations. I would just introduce the basic concept here, right? And the concept is you have your porous media flow and you have your fracture flow. You still don't really know much about the fracture network in terms of fracture density and stuff like this, fracture orientation, or at least not about separate fractures, right? There, you still assume there is some regularity to your fracture system, and you calculate, you know, your flow in your porous media, and you calculate your flow in your fracture network, and both can exchange through mass transfer. What that means is, for example, you have a higher pressure in the porous matrix than in the fractures, which means water is pressed into the fracture network. Or the other way around, you have your fracture flow, which is much faster than the porous media. So if the pressure in the fractures is higher than in the porous media, some of the fluid will be pressed into the porous matrix. But of course, how quickly things are pressed depends on the transfer term, which then, you know, you can set different methods, different ways of think about those kind of exchange parameters and how to parameterize it, what goes into those kind of parameters. right? You can have consider different assumptions and such as geometry of the fractures, geometry of the pore space, connectivity between fractures and pore space, fracture density, intact block size, grain size, bunch of things. Okay, here I just want to know you how it works, right? So there will be interactions between fractures and porous media considered here, right? Well, you can estimate what is my flow velocity in my fractures, what is my pressure in my fractures, and what is my pressure in the porous matrix, and they won't be equal necessarily, right? Which can be helpful information. Usually, for example, you can have the storativity in the porous matrix is higher than in the fractures. So you can also see, okay, under which conditions the porous matrix is transferring water into the fracture network where it's transported more quickly, and under which scenarios, for example, the fractures will have the water flow and then store the water in the porous matrix slowly and over time. Those are processes which you can study with the dual domain model, which you cannot study in the more simpler effective porous media model. Discrete fracture models, as I said, make sense usually if you know your fracture network very well, or if you want to study the effect of individual fractures. So you can believe that this is the most accurate method of studying flow through fractured formations. As I said, I not necessarily need to share this point of view, but you can take this kind of position. There are arguments for both sides. It's not only applicable if you know your fractures network by detail. You can also do something like statistical or artificially generated fracture networks based on statistical properties which you find for your fracture network in the field. Right, this is also things you can do. All right, so also then fracture representation, for example, aperture width. So you're doing some investigation of fracture aperture width in your studied area. If you have the possibility, you will get some statistical distribution, and you're applying this statistical distribution to your artificially generated fracture network. All right, remember what I already said is it can be computationally cumbersome, or you have quite a high data requirement. But yeah, you can really study the flow in individual fractures, and you can imagine, okay, maybe you have a geological setting where people are unsure does there is a fault or not. Well, you can run a model, incorporate that fault, see how your groundwater would develop. You can remove the fault, and you can see how the groundwater flow would develop. So you can get this scenario testing. This is what you do numerical modeling for, right? So it surely has its strong benefits. And you can also consider it having a different flow equation on the fractures than in the porous matrix. And you can also, again here, couple it with the porous matrix or not, the different kind of approaches. So a lot of possibilities to work on. All right, so we have something we call discrete fracture network models, where you would consider the matrix to be impermeable. Right, this often applied if you're talking about reservoirs in terms of geothermal or oil and gas, maybe. We can have discrete fracture matrix models where you have also flow in the matrix, and there is some coupling between both. And then you have this kind of equidimensional approach, means you are solving the fractures in their full spatial dimension. Right, so that's why I said before, usually we can simplify fractures as in one spatial dimension. So in a 3D space, we can represent it as a 2D, what would be the lower dimensional approach. But you can also do you can neglect doing this or avoid doing this. So you represent the fractures as they are in full 3D. But of course, this gives you high demands on spatial resolution or mesh generation, because if you have very thin faults, fractures, to discretize those with a full grid, that means you will have very, very small mesh elements. which then increases your mesh generation, but also your computational cost. But of course, this is the most detailed representation of those kind of fractures. On those nodes, you can separate them in the domains. We can separate those in terms of then mathematical equations applied. You can have different boundary conditions, all those kind of benefits which comes of that kind of effort. Or you can also, this would also be a discrete fraction network. You can have lower dimensional approaches where you then say, okay, I'm a 3D space and you still have my 2D fractures. But then still you would, represent those fractures explicitly in the model, just in the reduced dimension. And you could still solve a different kind of equation on those kind of fractures, right? Just going back to the lectures 2 weeks ago, we're of course talking here about unstructured meshes, right? So this is usually nothing you do with this rectangular meshes, right? Here we are in finite element, usually finite element models, or at least finite volumes, and very, very clearly unstructured meshes. Otherwise, you usually cannot represent that kind of dimensional and geometrical complexity. The embedded discrete fracture model is something that's not just that common, but I recently noticed that it gets incorporated in a few more of the commercial tools and also open source tools you can use for groundwater modeling. So it's kind of a combination. So you have this porous matrix flow and the fractures on top, and but you do not have this kind of domains continuously, but there is a constant interaction at the end of fractures with fractures and porous matrix flow. Okay, here you have this geometric reduction of fractures, right? So in a 2D space, 2D plane considered here, then you have your fractures as lines, right, with a start and end point and some kind of maybe aperture from which you then can calculate porosity and hydraulic conductivity. But this is reduced in the spatial dimension. All right. There are tools for this. It's a very interesting method. Has its benefits because you can also, you can similar things for the fractures as you do with the complete discrete fracture model, right? You can have it statistically distributed, or all your fractures by heart, by whatever method. You can parameterize it following statistical distributions, or maybe you have measurements, and you can still do, okay, like, does there is a fault or not? If there is a fault, what would be its effect? All those kind of considerations you can do, and you can incorporate that into your model, which is a very nice thing. But it's less computationally expensive than a full discrete fracture model. And of course, I focus on all the representations right now on the flow, but all what I said could be done for solute transport, for heat transport, right? You can see what could be the effect on the transport if there is a fracture, if there's not a fracture, all those kind of things. So summarizing the whole lecture, first part, advection, right? Consider that it is difficult, or can be difficult, to capture it accurately numerically. As a tip is avoiding the steep gradients. Remember that there might be numerical diffusion might occur, and well, that was very obvious in the examples I showed because I only considered advection. But if you combine with numerical diffusion with a regular diffusion, numerical diffusion, might emphasize this diffusive effect over what would be to be expected based on the physical process. And then remember those kind of particle models which you might come across in some tools, which can be helpful, but also might be computationally expensive. Second part of the lecture was the fractures, which we just finished. Remember that they require special care as well. And this is really a decision you should make on a conceptual model approach. Are fractures important? What kind of role do fractures play in the scenarios I want to look at, on the question I want to tackling? Are they important, and how do I incorporate them into my model? All right, this is really a question you should ask yourself on the conceptual modeling development stage, because then based on that you might choose a different modeling approach, a different software, which will be able, to represent that kind of fracture features. And remember those possibilities I just explained to you. Do you want to go for a dual domain approach? Do you want to have a discrete fracture model? Maybe an embed discrete fracture model would be, the intermediate solution. This is really decisions you have to make early on in your model development approach. So when you go for groundwater modeling flow, important question to ask yourself, to ask your client, okay, what about fractures? What size are they? What do we know about it? How important are they for the hydraulic processes we want to study? Thank you very much.